Ever since I was a kid, I liked rocks and fossils and stuff like that. And in junior high school, that's really what got me hooked on geology. We had a class that at the end of the school year went all around Ohio collecting fossils. And I really got into it. And um, after I was done with my undergraduate degree, I worked for a summer with the United States Geological Survey in Connecticut. And one of the guys said, "Hey, you want to go collect some fossil fish this weekend?" And I said, "Sure." So we get to this house, and this house is the backyard is lined with electric fence along the top. And inside the yard, there is an old van without any doors. And the guy gave me this great big pry bar and said, "Here, carry this and walk fast." I'm like, "Okay." And we get to the other side, and I hear this wolfing. And these two great big Great Danes came out of this van. It was their doghouse. But we collected fossil fish, and ever since then, um, I've been really interested in fossil fish, especially. When I was in grad school, I had the opportunity to study with a professor that was an expert in Green River Formation in Wyoming, and another professor that was an expert in taphonomy. Taphonomy is what happens to an animal after it dies, but before it becomes a fossil. And so I was interested in, how in the world do fossil fish get preserved? Um, so I started thinking about that when I was in Connecticut, and then worked on it some more when I was at Loma Linda. And in order to solve that problem, I collected a bunch of fish, fossil fish in Wyoming, and then I also did a bunch of experiments in my lab with dead fish because I wanted to see, what kinds of conditions the fish might be preserved under. And I tried all kinds of things. I tried deep water, shallow water, salty water, fresh water, water that was full of oxygen, water with no oxygen, and all kinds of things like that. Different fish species, different temperatures, and I really couldn't find anything at all that would stop the decomposition of the fish. In fact, the fish that were in the water with no oxygen, those fish decayed really fast from the inside out. And a lot of people say, "Oh, fossilization happens in the absence of oxygen," and that's absolutely not true. And that's been known for a long time by many paleontologists. But the the moral of the story is, and I've done the experiments with fish. I'm the world's expert in rotten fish, I guess now. But from the experiments I did, but decomposition happens fast in fish. Scientists have studied turtles. So my professor Leonard Brand was working in a deposit in Wyoming, and none of the turtles had heads. They were perfectly preserved, but the heads were missing. And so how do you figure out why? Well, he went into the lab. The same guy that did the experiments with the trackways. Not a surprise, right? He's just a really good experimenter. And he went into his lab and got some turtles, killed the turtles, and watched them in the aquaria, and they would fill up with gas inside and float. And the first thing that would fall off was their head. And then later on, they would sink, and the rest of it would be preserved. So I did this stuff with fish. People have done turtles and birds and insects and leaves and all different kinds of things. And the moral of the story is that whenever you find a fossil, whether it be a bone or a tree or a leaf or anything like that, uh, usually the only way that that fossil has any hope of being preserved is if it's buried quickly. Um, and oftentimes, even after burial, the decomposition continues because there's bacteria buried within the rocks. And so decomposition can happen, and oftentimes all that the rock does is kind of preserve the shape of the animal. And most of the time, we're finding, not all the time, but most of the time we think all of the organic debris disappears. We found some exceptions in dinosaurs and some other things where there's definitely some of the organic debris that's been sequestered and preserved somehow. But even when you have a shell, like a shell that you might collect along the beach, a seashell, um, uh, scientists have done experiments by putting bags of those things out in the ocean and watching what happens to them, over several weeks or several months at a time. And even those shells will dissolve. Uh, the detail on the shell dissolves. There's animals that come along and drill holes in the shells to get the nutrients out of them, and wave activity and current activity can break them. And so, even something as durable as a shell decomposes really fast. A few years back, some scientists wanted to study whales and how whales decompose. And so they got a dead whale, took it out in the ocean somewhere, and made it sink. And they went back a few months later to see what had happened. They couldn't find it. And they're like, well, maybe we mismarked it or something like that. And so the next time they got a whale, they took it out, they marked it, and put a camera on the ocean floor to watch what happens to it over time. And they went back some months later, and they were shocked to find that the whole whale is almost gone. And what happens is that organisms come from all over the place and just consume that enormous amount of organic debris that's there, even the bones. The bones get drilled into and consumed as well. And so a whale carcass, is almost gone after 6 months of time, even the bones. And so, that makes us think when we find fossils in rocks, and we're going to find some fossils here in the Redwall Limestone right here. It makes us think, how did these fossils get preserved? And we keep coming back over and over again to the fact that in order to make a fossil, you have to bury it quickly. If you don't bury it quickly, within days, it begins to decompose. I don't know if maybe I'm just weird, but if there's a roadkill on the road, I'll watch it over a couple days, right? If I keep driving by and see what happens to it, over time, and it disappears very quickly. Sometimes maybe somebody comes and picks it up and pushes it off the road just so it doesn't smell, but I don't think that happens very often. I think, coyotes will come along, or, something else happens, and those carcasses get consumed very quickly. So there are lots of fossils here in the Redwall, and one of the most famous fossils in the Redwall limestone is called the nautiloid. A nautiloid is like a squid. See, Miranda, I told you I was going to talk about ice cream cones. Here you go. You're missing it. A nautiloid is a squid that lives in an ice cream cone shaped shell, and this the end sticks out over here. The squid has 10 legs instead of 8, like the octopi does. I think I've drawn the correct number in there. 2 of them are a little bit longer. It's got an eye right here. It's got a mouth inside the tentacles there, and it has all these chambers in the shell. And these chambers are kind of interesting because the squid has an organ that goes right down the middle of its body that can adjust the amount of gas in those chambers. And so if it puts more gas into the chambers, what will happen to it? It'll go higher in the water column. If it lets gas out, it can sink deeper. And so the squid are hunters. They can swim really fast, and they're hunters, and they like to hang out at certain levels in the ocean, where the fish are going to be, and they'll swim into a school of fish and snag the fish with their tentacles and eat them. But anyway, the Redwall Limestone is famous for having fossil nautiloids in it. Just downstream from here is Nautiloid Canyon. And Nautiloid, we're not going to go into Nautiloid Canyon. It's a hard climb to get up in there, but on the floor of Nautiloid Canyon, there's just dozens of nautiloids, these guys, all over the floor. And we're going to stop at a bench alongside the river about a mile downstream that has quite a few of these in the rock. And I'm going to make you guys find them. I'm not going to show you where they are, but so we'll have a little bit of a scavenger hunt. But there's a lot in the rock down there. I think it must have been 25 years ago or now, something like that. Somebody challenged one of my professors, Dr. Steve Austin, about the Redwall Limestone. And they basically said this, you know, you creationists have been doing great work in the Grand Canyon, but you're never going to be able to show that the Redwall Limestone was made quickly, because everybody knows it was made in a calm and placid sea. And you don't tell Dr. Austin something like that and expect nothing at all. And so he had been on the river a number of times, and he organized a river trip to come down here. It lasted several weeks, I hear. But they stopped at places like we're going to stop at just down the river right here. And they got their Brunton compasses out, and they measured the orientation of all these nautiloids. They measured it at the bench we're going to stop at. They went into Nautiloid Canyon. They hiked up a number of side canyons in Grand Canyon up to the bottom of the Redwall. That's where these nautiloids are. Measured the orientations there. Went far to the west into western Arizona and into Nevada, and continued to trace the nautiloid bed out. It starts right down here, but they've traced it, you know, all the way out to Nevada. And there's some really interesting things that happen to it out there. But in the middle of this nautiloid bed, and it happens to be called the Whitmore nautiloid bed, not after me, but it was originally named and described in a canyon called Whitmore Canyon. And Whitmore Canyon is actually the canyon that we're going to helicopter out of, and it's the canyon that Bar 10 Ranch is in. So anyway, as you're flying in the helicopter, look out the window, the bottom of the Redwall nautiloid bed's in there, right? The Whitmore nautiloid bed. And the Whitmore nautiloid bed kind of looks like this. It is a unit that's about 6 or 7 feet thick, and the nautiloids are right in the middle of that bed. You don't find any usually at the bottom or at the top. They're usually right in the middle of the bed. And there's some other features in here as well. There's a bunch of vertical tubes that you'll see filled with calcite in this bed. And some of them can be quite big around, but that's another feature of it. And sometimes in with the nautiloids, you'll see heads of corals and other things in there. Well, Dr. Austin measured all these nautiloids. He found out that they have a preferred orientation. So when you take a long object like this and put it in a current, the current will orient it. So you can see there's some sticks on the bottom of the river right there, and notice how they're oriented. They're oriented with the current. And nautiloids and tree trunks and other things will do that if they're in a current, either parallel to the current or perpendicular. And it'll have a preferred orientation. And so Dr. Austin was able to measure all these sites, and he was able to demonstrate over the length of the nautiloid bed that these nautiloids had a preferred orientation. And in fact, he estimated there were over 6 billion nautiloids in this layer. And that's a minimum estimate. 6 billion, that's billion with a B. And you'll find one when you find the nautiloid bed. You usually find a nautiloid every square meter or so. Just a lot of them, right? And so I was at a geology conference, and Dr. Austin usually goes to these conferences too. And I was at a geology conference, and word got out. It's a secular geology conference, but word got out that there's this young Earth creationist, right? The worst kind of creationist, the young Earth creationist, was going to present at the geology conference. And so this room that had 300 chairs in it had 600 people. There were people lining the aisles and, you know, standing along the wall and even encroaching onto the stage and stuff like that where he spoke. But he gave this talk about the nautiloid bed, showed the orientation studies, was able to demonstrate these tubes that I mentioned. These are water escape features. And so if you take a sponge that's filled with water and you squash the sponge like that, what happens to the water in the sponge? It'll shoot out, right? Well, he was able to show that these features right here are water escape features. And then he was able to show a model of how this bed formed. And so what he thinks is there was almost how do I describe this? Almost like a layer of wet cement that moved very quickly along the ocean floor. And as this moved along, it would move fairly quickly at meters per second, but it would generate this current up ahead of it that would catch nautiloids that were swimming, catch them alive, and bury them inside this bed that was moving along. And he had some videos that people had done laboratory experiments to show that this kind of thing was reasonable and so on. And this particular bed could form within seconds, and he estimated it moved from like Colorado to California, and captured all these nautiloids and buried it. And then this current was flowing in this direction, and whenever you have a current flowing one way, there's a counter current. Look out here in the river. The main stem of the river is going that way, right? But did you see how it's moving right here along where the boats are? It's moving upstream, isn't it? There's a counter current. And Dr. Austin thought that because this was such a strong current moving this way, it's going to develop a counter current moving the other way. And you notice all the striping that's in the Redwall back there? We just went by Tiger Wash a little ways past, the same thing. He thinks that striping is made from the nautiloid bed being deposited really, really quick. And so he presented all this at that geology conference, and after he sat down, there was just silence. And everybody realized that at least the bottom of the Redwall is not a calm and placid sea. This is limestone and dolomite right here, and most geologists are taught that limestone and dolomite accumulates very slowly. But he was able to demonstrate without a doubt that at least the bottom portion of the Redwall was made catastrophically. Just an amazing study. That was by Steve Austin. What we're going to do is I'd like you guys to go through this rock pile back here, and there might be some surprises in there. See what you can find fossil-wise. There may be some nautiloids in there, but more likely you're going to find some crinoids and some bryozoans, perhaps a brachiopod or two, some corals, and some things like that. And after you guys look around here in this pile and you can photograph some things, we'll go down a mile downstream and look at the nautiloid bed as well. So we'll be looking at this portion. I'd like you to find the nautiloids in there, but also look for these water escape structures as well. That's certainly an important part of the story. Okay? All right, see what you can find.
John?
Yeah.
What was it again that you said
It's the counter current coming back the other way.
So the white would be one direction and the red would be a different direction?
Maybe not. Those are layers of chert and limestone and dolomite in there. But we're not sure if all that can be made by a single current. It might be, and just sometimes things can self-sort after they're even laid down. So that might be part of the story. I'm not sure.
Okay.
But